Hello, everybody. Today we will continue with our lectures. As you see, what is new, we have slides. We have slides in English, which is very good for us. So you can also look at the slides without needing to translate them. So before we start, there was one question about the examples of the exam. So through these lectures, we will show one exam and we will solve it. So then you will have the whole information about it through our lectures. So today we continue with signal flow graphs. Signal flow graphs is something what we will need to use for the analysis of filters. Before we were learning about filters that are from passive components, and now we will continue with filters that use active elements. Okay, so what is signal flow graph? Before we continue, I will plot you some interesting example. This is called block diagram. How it looks like. For example, if you have following blocks, then you will be able to design the feedback system like this. And here is the question in the block diagram, which is the transfer function. For example, V out over V in. And then everybody knows how to calculate it. For example, we must here put some auxiliary variable, we call it epsilon, and then we can write the equations to solve it. So what is of our interest is transfer function V out over V in. So this is our goal. Okay, so what is epsilon? Epsilon is V input minus beta times V output. And what is V output? V output is epsilon times H of S. So these are the two equations which we will try to solve. So we can write V out is equal to V in minus beta V out times H of S. So V out is 1 plus beta H of S, which is equal to V in times H of S. And then finally, we can write T of S as V out over V in of S as H of S divided by 1 plus beta H of S. So as you see, by using this block diagram, it's not so simple, but it's something what we already know. If we replace by signal, just a second, signal flow graph SFG, we can plot the same diagram in a much more simpler way or representation. For example, we can have node V input or this can be voltage or whatever else, current. And then we have transmission. We have transmission H of S, and we have minus beta as the gain of the feedback. Here is V out, and here is our auxiliary variable epsilon. So as you can see, this what was block diagram can be represented by signal flow graph in a much simpler way. So these two things, they are equivalent. So they are, let's say, they represent the same thing. Okay. But now we want to try to calculate T of S using signal flow graph, and this can be done using some rules. Rules are, we will derive them later. Rules are, look at the path from input to output. This is H of S. And then look at the loop, which is on this path. This is the loop. The loop gain is minus beta times H of S. So here comes 1 minus loop gain minus beta times H of S, which is indeed the same result as we got it earlier. So this is our solution, H of S over 1 plus beta H of S. Before we continue, we just compare these two approaches. First approach was block diagram. We have to calculate everything. Second approach is signal flow graph for the same thing, but it looks more simple and it can be solved using some special rules. I have applied the rules now immediately, but we will learn the rules now. So this was just a demonstration how quickly we can get to the same result and how simple our representation is. Okay, so we continue with definition of signal flow graphs. This is a method of graphically displaying a set of linear equations. For example, here we had two linear equations, and we have described them by this here signal flow graph. So these are the same equations which are valid for both approaches. Okay, so here is also on this slide is also one example of equation. And second one, we have here two equations which are linear equations, so they can be represented by signal flow graph. What we must learn in signal flow graph is what is node. All these are nodes. For example, here, these nodes are here, 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 everywhere. So these are variables or signals. They are represented by nodes. Then we have branches. This is branch. This gives dependence between two nodes or two variables. Then we see the source node. This is source node. This is also source node. This is not source node. This is node with no branches entering, like this. These are independent variables, but X0 is not independent. Now, what is sync node? This is this guy here. Node with no branches leaving. So this is variable that no other variable in the system is dependent on. Okay, so here is another example. We also can define something which is called open path. For example, A, B, C, D. This is open path. This is also forward path. A, E, H, D. Then we recognize loop. This 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 here is loop A times F. But e.g. F is not loop. Why? Because it is number 8. So we will not consider this as loop because this is number 8. Self loop is feedback consisting of signal branch. This is G. This is this one. This is self loop. What is branch transmission? These are these letters applied on each branch. And what is loop transmission? For example, E times F is loop transmission. Okay. We also recognize some rules which connect our signal flow graph with linear set of equations. We have told already that signal flow graph is connected with set of equations. So the variables at the nodes are associated with the variables of a set of linear equations. Signal travels along branches only in the direction of the arrows. It cannot go back. Signal traveling along any branch is multiplied by the transmittance of that branch. So, for example, x1 is A times x0. So this is very, very simple. This transmission A multiplies x0 to obtain x1 and so on. So this is very, very logical and you can see it. Value of variable represented by any node in the sum of all signals entering the node. So we can say that this here, for example, x3 is C times x5 plus H times x2. So this is very obvious. So we don't need this summation. Instead, when we go into this node, the summation of signals is something what is assumed. So the value of variable represented by any node is transmitted on all branches leaving that node. Okay. So this set of equations correspond to the signal flow graph on the previous slide. So you can check it and see if it is if this picture here corresponds to this set of equations. So you can stop your recording and then try to rewrite it. Okay. So we can say the signal flow graph of the network depends on the set of equations used to describe that network. And of course, here on the right side, we can also conclude that it's more simple, much more simple than using block diagrams. Most of the people are used to use block diagrams, but we on this course, we go one step forward and we will use signal flow graphs. Okay. Now, there is some special application of signal flow graphs. It's not only the calculation of transfer function, they can be used to build networks. Now we will see, for example, what's going on here. Okay. I have some simpler slides and I will show you. So instead of all these slides, I have some a good example and you will see immediately. These examples are in Croatian language. So here, but it doesn't matter, we just look at the example. Here we have some passive filter, as you remember, we were learning passive filters last time. So it has inductances, it has capacitances, and it has resistances at the ends. So this is typical ladder filter. And then if you want to describe equations of this ladder filter using Kirchhoff laws and voltage to current relations, then you have the following set of equations. So what is V0? V0 is this here. This is voltage of the RS, and then this is Vs minus V1. So it's obvious. And what is Is? It's V0 divided by Rs. So then we can just replace V0 by Vs minus V1, and then we have such a equation. Then we can calculate current I1. I1 is summation of Is minus IL2. Then we write what is the voltage V1. This is 1 over SC1 times I1, and I1 is these two currents, and so on. What we see, we always have multiplication by 1 over S something, SC1 or SL2 or whatever. So this is integrator. And then we can describe this by such a network. Let me see if I have it in English. This is similar drawing in English version. So you can see immediately here that all these equations you can recognize here. So here is what is V2? What is V2? So V2, if we look, it's dependent on I3 and I1. This is 1 over SC2 times I1 minus I3. So this is typical integrator, and so on. All we have to notice here that some of these this is -1, some are negative and some are positive. So this is something what we have to notice. Now the question is, how can we design this network which is described by such a signal flow graph? So this signal flow graph describes set of equations. They are here. This is all these equations. And then this is also signal flow graph, the same. And then we would like to have all here voltages. How can we do that? Before all, if you see some branches, for example, this can be V0, this can be V1, this can be V2, and so on. It has nothing to do with this here. Okay. For example, if you have here 1 volt, here you have 2 volts, here you have again 3 volts, and so on. If we want to increase this to have 4 volts here, for example, or let's say we want to multiply this by 2, how can we do it? So if there is here transmission A and here is transmission B, the most simple way to do it, to raise 2 volts to 4 volts, is to multiply this A by 2 and to divide this B by 2. So V0 and V2 will stay 3 and 1 volts, and this guy here will go to be 4 volts. So we can accomplish it by multiplication of input by this value of 2, or dividing output branch by this value of 2. So everything else stays the same, but only this middle node. Let's say this, we call this value of 2, we call it lambda. Okay, so the rule is, if we want to increase some node by value of lambda, then we multiply by this value of lambda all incoming nodes, and outgoing nodes we have to divide by lambda. Okay, we can do it. Just a second. We can do it here if we multiply all these nodes by R0 like this. Okay, then we will have here and here all the voltages. And next, what we want, we will see now very quickly. You probably remember our op-amp circuits. For example, if we look at the circuit like this, then we will have a so-called integrator. So this is R1, C1, V out, V in 1. What is V out? It's this impedance here divided by this impedance here and minus okay, this is minus Z1 over Z2 times V in, and minus sign, because here comes the signal, and this is indeed minus Z1 is 1 over SC1 and times R1 times V in. So this is called integrator. So this is the simplest possible integrator circuit. The next important circuit which we also recognize is the following one. We have V in 1, V in 2, R1, R2, and we have R0. And then we have V out, which is equal to minus R0 over R1, V in 1, minus R0 over R2, V in 2. So this is the, if we choose R1 to be equal to R2 to be equal to R0 to be equal to R, then we obtain V out as minus V in 1 plus V in 2. So this is kind of summation and multiplication by minus 1. This is summer or addition circuit. Okay. Then the next guy, which is also very useful, is called inverter. So if you use two same resistors here, which are called R0 and R0, then V in turns into V out, which is equal to minus V in. This is, so let's say, multiplication by minus 1. This is inverter. Okay, and then if you put this inverter here at the end of this integrator, then you don't have negative, but you have positive integrator. And another very useful thing is to combine some summator and integrator. So, for example, if you add here R2 and V in 2, Then here, this is V in 1. You can add, just a second. This is V in 1. You can here add minus SC1 R2 V in 2. Okay, so this is combination of summation and integration together. Good. Now let's see about these -1 and +1. What we need, we would like to have all positive numbers, not -1. We want to have here +1. So after some transformation of the network, we can have all positive here, and then we can try to use all this circuitry on the right side to build the network. For example, this guy here, together with those two resistors, this is the same like this here. So we have summation and integration together. Okay. Here also we have possibility to, with inverter at the end, to obtain positive integrator with summation. So all these branches that are negative are here, and these integrators that are positive are here. So starting from the passive RLC network, using signal flow graphs, we have derived active RC realization of the filter, which is shown here. So this was one of the very useful observations we could do using signal flow graphs. Now we can continue with Mason's rules. What is the Mason rule? So there are two rules. One is single path reduction, and another one is multiple path reduction rule. If you have signal flow graph with a single forward path between its source and sink node, then forward path must touch all the loops of the signal flow graph. So let me see how it looks like. This is example. So what is graph determinant? This delta. This is 1 minus sum of all loops plus sum of products of all non-touching loops taken 2 at a time minus sum of all non-touching loops taken 3 at a time, and so on. So this is a rule how to define this delta in the denominator. Then in the numerator you have path from the node I to the node J. So this is in the numerator. So as you see here, this path is A, B, C, D, E, F in the numerator. And then here you have loop 1, loop 2, loop 3, and so on till loop 5. And then you have multiplications of pairs of non-touching loops. Which are non-touching loops? L1 and L3. And then L1 times L4. And then L1 times L5. They are all non-touching. Also, L2 is not touching L4. L2 is not touching L5. And L3 is not touching L5. So these are all non-touching loops. And then what is missing here is minus sum of all non-touching loops taken 3 at a time. This can be minus L1, L3, L5. So this is what is missing here, because we have 3 non-touching loops. So we have assumed that to apply this Mason's rule, the path P from the input to the output, from the source to the sink, they must touch all the loops. This is example. If you have such a network with 4 impedances and voltage source, then you can, as we did a moment before, you can add the signal flow graph to this network, and then you can write, for example, what is V2 over V1. So what is important that this path from V1 to V2, this touches all loops. We have 2 loops here. This is one loop, and this is another one loop. So you have to touch both of the loops. What does it mean to touch the loop? So for example, this Z2 is the same for the path and for the loops. Okay. What is delta? How is delta calculated? So we have this loop here. This is minus Z2 over Z1. 1 plus 1 minus and minus comes here, 1 plus Z2 over Z1. So you can recognize it very simply. Here also there is a loop, minus Z2 over Z3 plus Z4, that's this guy here, and then you have minus times minus, it's plus. Now the question is, what is the transfer of from V1 to V4? This is in the numerator. You must multiply all these transmissions. So this is 1 over Z1 times 1 over Z2, and so on, Z4 over Z3 plus Z4. So, and delta is in the denominator. So as you see, using these rules, it's very simple to calculate transmission. You can try to do it in another way, so you will see that any kind of other calculation will be more complicated. Now, the last question is, can we apply this rule to calculate I1 over V1? The answer is no, because from V1 to I1, we don't touch the second loop here. So because we don't touch it, we cannot apply this rule, but we will find what we can apply. Okay, in the second example, it's also very simple path from X1 to X6, which touches all the loops. And here we have a little bit extra loops that they are not touching. For example, this loop here does not touch this loop here. So you have 2 non-touching loops, C, F, E, H. And here is loop B, C, D, G, and C, F, and E, E, H. These are all loops, and then we look who of them are touching. Okay. Now we have a second rule. I will derive it very simple here. So here is X1. You have A. We know now how to do it. This is G. This is C. X6. So we can apply the first rule. What is X6 over X1? This is equal to ABC, 1 minus BG. This is first path. Second path, this is this guy here. The first was this guy here. Second path is equal to E, H, D, F, and then this is first, X6 over X1, second is DEF 1 minus EH. Okay, now if we want to add contributions of both parts, this is C, A plus B, then you can write x6 over x1 as ABC 1 minus BG plus DEF 1 minus EH. And then if we write them together, 1 minus BG, 1 minus EH, ABC times 1 minus EH plus BEF 1 minus BG. And if we particularly look at this part here at the bottom, then we will recognize that this is equal to 1 minus BG plus EH plus BGEH. So this is something what we know from before. So this is this delta, but this thing up, because you have two independent parts, this has special rule, which, okay, this is the same delta as here, as before, but then you have two transmissions of the two parts. So, and you have two cofactors. This first cofactor, and this is second cofactor. This is determinant of the part of the signal flow graph that doesn't touch. So you can check we have derived the same transfer function. So this is called the second, the Mason's rule, and it's general, and the special case of this second rule is the first rule. So now we know how to use rules. Here are some examples. So in these examples, you can see that sometimes we can use the first rule, sometimes we can use the second rule. So here we can use the first rule, ABC over 1 minus BE plus D. So there are no non-touchable loops. They are all touchable, and that's it. Here, for example, you have two paths. You want to come from I to J, because here you have one loop which is non-touchable. Then you must consider it as a second rule, and then you can you have these cofactors here. And then also here in the third example, you see you have two paths. This is the first, ABC, and then the second is A times F. So you have two paths. ABC touches everything, but AF doesn't touch this loop D. So you have minus 1 minus D. And here in the numerator, you have also all the loops, because they all touch each other. Okay. You can look at these examples also, and then you can check if this is all good. Okay. Now we continue from transfer function to signal flow graph. Now we'll try. So till now we were able to derive transfer function using signal flow graphs, but now you will go other way around in the opposite direction. We know transfer function, and we want to plot the signal flow graph. So we want to make some synthesis, not only analysis. Okay, it's good to start from the given continuous time function in S. What I forgot to tell, these signal flow graphs are effective in the S domain, but they're also effective in the Z domain. So they are applicable to analog as well to digital systems. So they are very, very useful. If you have analog system which has continuous time function in S, then it looks like this. And we can assume that this numerator and denominator order are the same. And then we can divide everything by S to the power of n. We will obtain this. And finally, we will be able, using Mason's rules, to derive how it looks like. So we have two assumptions. Every path touches every loop. then all deltas are equal to 1. So here we don't have anything, just 1. And all loops touch each other. This is another assumption. So it will be only this in the denominator. We will not have this, and this will be 1. Okay. So this permits two direct representation of T of S as signal flow graph. Okay, you recognize this probably. This is called direct form 1. What is we have three paths. K times A0. This is this one. Then we have K times 1 over S times A1. This is this one. And then we have K times 1 over S squared times A2. This is this one. So all these three paths, they are added. In the denominator, you have 1 minus these gains of the loops. Okay. We can also write it in different form. You will have the following representation. And now at the end of this signal flow graph representations, we will try to explain how can we use signal flow graphs in analysis of op-amps. For example, if you plot an op-amp, you know here in the op-amp inside, this is voltage source. And this is equal to A times V plus minus V minus. Of course, A is going to infinity, but this is not so important now. So this is V out. We can plot it in the same way, in the following way, to obtain the same equation, like this. This is A. This is V plus. This is V minus. This is minus A, and this is V out. So this was enough to represent the op-amp. Now the following example, which you can see here, if you put at the output of the op-amp, if you put something what is called a voltage divider, R2, R1, this voltage here is equal to V out times R1 over R1 plus R2, which we will call T32. And then we can connect it here. Our question is, if we put here V input, what is V output? Okay, so we can add this transfer T32, and here we can put V in, and we will now obtain the transfer function, which is equal V out over V in as. We start with the signal from here. This is 1. And we go here. So it will be in the numerator A. In the denominator is, because we are touching this loop here, this loop has a gain of minus A times T32. We have here 1 minus loop. This is loop L1, which is equal finally to 1 minus A times T32, and which is then equal to A1 plus T32 times A. So this was the calculation of non-inverting op-amp using signal flow graphs. As you see, this helps a lot to make analysis of such a circuit. And what is the next move? The next move is to include this guy here. And then we will have A over 1 plus R1 over R1 plus R2 times A. If we divide everything by A, we obtain this. And this goes to 0. If A goes to infinity, then you have R1 plus R2 over R1 if A is going to infinity. So we have found the gain of this non-inverting op-amp if the gain is going to infinity, but we were using our signal flow graphs. Also, signal flow graphs can be used in the following schematics. For example, if you have RC network and some gain, we will use it next hour. And then here are some more examples of using signal flow graphs. For example, if you have a gain amplifier here, then you have the various ways of representing the signal paths. Okay, so for now, okay, we can write T of S as 1 plus R2 over R1 in this first non-inverting example. Okay, now we will make a break for 15 minutes, and then we'll have a second hour with the next topic. So we'll see us after 15 minutes. Stay tuned. Hello, we continue with second hour of today's lecture. So we will talk about active RC filters, and we will see how they are organized and how they work. In doing so, we will also use this what we have learned from the first hour today, which is signal flow graph. So you will see that this is also very useful for describing active RC filters, not only passive filters. Okay, so if we remember from the last time, which we have learned, is that passive RC networks can only realize poles which are negative and real. And now we'll see what we have to do to obtain complex poles. Before we continue, we will define basic terms which we will mention today. This is biquad. This is then single amplifier biquad, because these biquads with single amplifier are most simple, and we'll start from them. Then we'll talk about root locus diagram. What is root locus diagram? Everybody who was learning control system theory, they know it. Then we will use signal flow graphs, which we have just learned, and then we'll talk about circuits with single feedback, double feedback, and so on. Asymmetrical input, differential input, and we will always, in most cases, use asymmetrical output. We will talk about filter characteristics like low pass, high pass, band rejection networks, and all pass networks. Okay. Now, if we look at some example of the, let's say, elliptic filter function, it could be 7th order, 6th order, or whatever. We can break it into quadratic terms. For example, this is 2nd order term here, and we can combine it with these zeros here. So poles and zeros can be obtained from a computer program. We can say that elliptic transfer function, it has finite zeros that are here. You see, this is finite zeros. And poles are here, like by Butterworth or by Chebyshev. Okay? And then if we look at the amplitude frequency characteristics of this transfer function, you can see how it looks like. It has equiripple in the pass band and equiminima in the stop band, and it has transition band. Okay. So our network will be designed in the following way. So we need to realize those, for example, complex conjugate networks, poles, like this. If we choose them in pairs, then we can realize each pair. But now we also have to see, so this, how these networks will be realized. So for our 7th order, this is going to look like this. Okay, this, if you have odd order, here is resistor, RA, CA, this is one, let's say, one first order network. Okay. In designing of cascade of biquads, we can merge, we can combine poles with zeros. So we will need a circuit which can realize finite zeros. And the rule of thumb is to pair zero, which is nearest to the highest pole, highest pole Q value pole, and then the lower pole Q value is combined with the next zero, and so on. So this is the rule how to obtain maximum dynamic range. Also, it's important to distribute gains. This is something what we will see so this is something what we will see later in some examples. And then as the third step, it's important to select sequence of biquads for maximum dynamic range. For example, T 2 is first if it has the highest pole Q, and then comes next the T1, which has lower pole Q, or T3, which has the minimum pole Q. Okay, and now the question is, you recognize here immediately our block diagram. Sometimes it will appear, but in most of time we will use signal flow graphs. Here you can see how we can obtain the feedback, and how we can obtain complex conjugate poles. This is our basic picture of the circuit. Okay, so as you all know, the passive RC network has the following poles. They are here on negative real axis. This is all what we know. Here, if you apply a transfer function, mi of s, in some feedback of some gain device, the gain of the device is equal to beta, and then probably we have negative feedback. Then this mi of s is passive RC network. K is also another network, and the transfer function V out over V in looks like this. Is K times beta over 1 plus beta mi of s. Mi of s is, let's say, transfer function of some passive RC network, and this has its numerator and its denominator. We will use the following notification for the passive RC networks. For example, this kappa will be used over any notation. D of s is denominator of transfer function of mi of s. So this is, let's say, passive RC network. Okay. If we introduce this here, we can write K times beta over 1 plus beta n over d, which is equal to K times beta d plus beta n. And this is K times n over s, n of s over d of s. Okay, so what is d of s? D of s is denominator which will be obtained. And if d of s is equal to 0, we obtain poles. D of s is d kappa plus beta n of s, which must be equal to 0. And then we obtain the following equation. This is called characteristic equation. So when this characteristic equation equals to 0, then you will have poles. We start from beta, which is equal to 0. And we finish when beta is equal to infinity. So if beta is equal to 0, then we have only d of s equal to 0. If beta is getting larger, then n of s is becoming more and more influential. So then we will have the following shortcut, n of s is equal to 0. So we can say that our root locus will start when beta is equal to 0 from the roots of the d of s, which are indeed roots of these negative real poles, because they are poles of passive RC networks. And then we can also rewrite this in the different form, which is equal to beta n of s is equal to minus d of s, and then beta n of s over d of s is equal to minus 1. So if you write it in this form, then it is very well known characteristic equation. It's called 180 degrees root locus. And this is because of this minus 1. Minus 1 means 180 degrees. So this is where the name comes from. So the following problem is defined. We want the following situation. So we start from the roots of d of s, which are negative real poles. And what we want to put somewhere roots of n of s, because root locus starts from d of s and finish in the zeros, which are the roots of n of s. So for example, if we put some zeros here, we expect, so this is beta equal to 0, this is beta equal to infinity. We expect, if we change the gain beta in this, let's say, in this schematic, this is the gain. If we increase from 0 to infinity, then we expect to have such a root locus like this, and that it will go somewhere into complex plane. So what we want to have is not having these here, not having those two, but having the poles here somewhere, which are conjugate complex. So this is our goal. Okay, now the question is where to put and how to put these zeros to obtain that our poles for some gain beta will become complex conjugate. So this is the topic of our today's talk. Okay. So here is the problem formulation. We want to obtain complex conjugate poles, which indeed have pole Q, which is larger than 1/2. So this is a general signal flow graph with one active element beta. And what we are going to research is this denominator, which we have already written. And then we can say that this is simplified signal flow graph of our system, and then we will research how this gain beta, which can be positive or negative, how it will influence the position of poles. Of course, if we write d of s, then if it is plus, then it's negative feedback, and if it is minus, then it is positive feedback. Now we can try to calculate the new Q, which must be larger than 1/2, and this Q kappa, it has smaller than 1/2 pole Q. Okay, this is larger than 1/2. Okay. Now, if we write our characteristic equation, we recognize that here we have z and z prime, and we have p1 and P2 here. Okay. Now the question is, what's going on if we have negative feedback? How our root locus looks like? We will see very simply that this picture shows us all possible position of root locuses and zeros, and these number 1, 2, and 3 are the most important. So the rule says like this: if you have negative feedback, which is this here, the rule will say that the part of the root locus which is on the real axis, this is this one here, is on the left side of odd characteristic frequencies. What are characteristic frequencies? These are zeros and poles. For example, these are poles and these are zeros. So zeros are up somewhere. So left on the first pole is this part of the root locus, which is indeed what we need, because if the beta is going to be larger than 0, then it's going one to other, and then at some moment it will go off the real axis and they will become complex conjugate, the poles of the closed loop. Okay. Now we can see how this is accomplished. This can be done if you have one RC network which is in the feedback loop of the gain, which can be positive or negative. For example, here we are researching negative feedback. If you plot RC network which has two inputs and one output, we can this is number 4. We can also calculate transfer function, for example, T1, 2 as V2 over V1 when we just a second. This is 2. 2 is output, V1 and V3 are input. This is output. So we can calculate when V3 is 0, so this guy here must be grounded. Here comes a voltage source, and here is V2 as V output. This is something what we will call transfer function from input 1 to output 2, and this is calculated when V3 is 0. Also, we can calculate T32 when V1 is grounded and V3 is V input. This will be V2 over V3 when V1 is 0. But why I write it? Because this, if you have the same network, then these two transfer functions, they have the following properties. They have numerator and 1, 2 over D1, 2. And this guy has N3, 2 over D3, 2. And if it is the same network, let's say single RC network, the following is very important to notice. D12 is equal to D32 is equal to D of S. So denominators of all transfer functions are the same. So this is very important to notice. Now, if we look at the negative feedback, here is positive sign. Here is our signal flow graph of the circuit with negative feedback, and here are the transmissions of each of the transfer function. Here is this statement, which is not so expressed to be visible like here on the right side. And if it is with the same network, then the denominators are the same. So we can say those denominators can be then merged together, and then we have the following equation. Okay. Now we can say, if we start from D of S, which has Q kappa, which is smaller than 1/2, we must find beta, and numerator that we obtain Q, which is larger than 1/2. Or we can plot it like this. So we ask ourselves, how can we move the negative real poles into the complex X plane? Now, a characteristic equation for the root locus with respect to negative feedback looks like this. As you remember, we said for this negative feedback, the root locus exists on the real axis on the left side of odd characteristics frequencies. Okay, this is exactly what is here. What is here written. This will tell us where we can put the zeros. For example, if you put 1 0 here, what will happen? It will happen then that you will have a root locus here, and you will never probably go to the complex conjugate plane. So this is exactly the problem to be solved. So what we can obtain, this is explained very easy in the following way. If you have zeros, so we always start with poles of the passive RC. If we have zeros somewhere in infinity, like this, then the following will happen. The root locus will go like this. So we are now sure that it happens on the left side of the odd number. This is 1. P2 is only 1 pole. And it goes to the infinity, because zeros are in infinity. So this is this blue here picture. It can also be possible. So this is number 1. Number 2 case is if you have, okay, we start with the same picture. If you have 2 poles, and if you have 2 zeros which are in the origin, then you can make such locus, which will also finish in zeros, like here, because locus always finish in zeros. So we are again on the left side of the odd number, because we have 2 zeros here, 1, 2, and here is 3, and left of the third characteristic frequency, which is P2, we have the root locus, and then it can go out. So this is situation number 2. It is also possible to have situation number 3 like this. So this is 3, this is 2. If you have the following situation, and if you start from the P1 and P2, if you put your zeros somewhere here, then again you will be on the left side of the odd number, and then you go here to finish in zeros when beta is equal to infinity. Here is beta is 0, here is beta infinity. So we have shown here all 3 possible situations. What we need is indeed these, for example, for some beta, these 2 poles which are conjugate complex. And this is what we want. And here we started from negative and real poles. And that's it. That's whole story. Okay. So here on the following slides, this is plot a little bit more fine, so you can see it. Now the question is, which function will give us zeros here? I can say immediately that this is T32 to be low pass function. So if the transfer function has this form, that means in the numerator it has s to the 0. This is low pass. And then, of course, if T32 is low pass, then you will have zeros here in the infinity. So this is something what we remember from before. Okay, so this is zeros here. Okay. We will call this class 1, but forget about this. What is important to note is that T32 in the feedback, it makes that the root locus is going up to the complex conjugate plane. Okay. This is number 3. How this can be done? Like this. So this is low pass transfer function. You can calculate it, but it has the form like this. These RC networks, and if you have negative beta, and this is the low pass transfer function. The signal starts from here and finishes here, and the feedback goes from here to here. You can try to calculate how it looks like. R1, R2, C1. C2. Okay. So now the question is, where can we put signal? Like this. So if you want to drive such a filter, then you have to cut this C1 and put in series voltage source. Nothing will change. The transfer function will be the same as we put here the voltage source. But we will have, from here, we will have feedback. And here we will have input signal. And of course, if we put this all together in the feedback loop of amplifier, then we will obtain the filter, which will have complex conjugate poles. And this is the old story. Our our circuit will look like this. Or if we try to realize by using op-amp, it will look like this. Okay. Now we can calculate zeros and poles, especially poles, which are without this. This is lower than 1/2, and this here is higher than 1/2. So we can see that they are connected here by this equation, and it is because beta is growing larger than 1, then you will have immediately the pole Q, which is larger than 1/2. Okay. This is also a possible variation. Here we had bandpass filter. Now we can also see that it's possible to add one resistor together with this voltage source, and you have the following circuit. By this we have created low pass filter, which has complex conjugate poles. So this is situation like this. Situation number 1. This here is situation number 2. Okay, let's see how it looks like. So if you tune R beta, you will go with different beta on the different positions of poles in this root locus. So this is obtained the voltage controlled bandpass filter with variable center frequency and constant bandwidth. What are the advantages or disadvantages of such a network, which we call number 1? So omega depends on the gain, which is not good. We want omega to be independent of gain. You see it here. So this omega will be better if it is not dependent on beta. But for this circuit, this is just a theoretical circuit. This is obviously dependent on beta. Pole Q is always needed to be high, and then this high pole Q is obtained with very large betas, and this is also not so good. It would be better without this square root to be proportional to beta. And only low pass and band pass filters are possible. Now we go to class 2. This is this one here. So what we need in T32, this is called high pass. You remember that high pass has S square in the numerator. So if the network in the feedback is of high pass character, then it will be root locus like this here. Okay. So how this high pass network looks like? This is low pass network, but high pass, probably you will remember immediately. This is like this. This is V2. This is high pass. This is low pass. Okay. If this voltage source is here, then we have such a picture. So this is what V3. High pass will give us, as I have told, will give us this root locus, and it will be possible to obtain poles that are somewhere here. If we try to calculate for omega p and qp, we will see immediately that we have obtained complex conjugate poles, because this q kappa is lower than 1/2, but if we multiply it by this factor here, it will be without kappa, QP is higher than 1/2. Okay. We can also obtain two versions. One is bandpass and one is high pass. Here we can enter with the signal, or here we can cut R1 to enter with the signal, and then we will obtain the following circuit, which is here, and of course, which has this transfer function in the feedback, which is high pass. Okay, so at the end we will conclude the character of the whole filter is defined by this transfer function here, and the class of the filter regarding where is the position of the root locus is defined by this T32. So T12 determines character of the overall transfer function, or let's say closed loop transfer function. Okay, so here if we can see that if we increase the gain, our poles are coming more and more close to this place, which is origin, and our conclusion is that omega p is getting smaller and smaller, and we can obtain very small omega p factors, which is not possible using other techniques. So here you see that omega 0 is divided by 1 plus beta square root. And of course here QP is also larger than 1/2, which is obvious. Okay, so here we can also look at the advantages or disadvantages of this class 2 networks. So this is 1, this is 2. It will be good that omega 0 will depend not on beta, but only on RC, but it's not the case. Of course, again, like in the class 1, it will be good that QP is proportional to beta, not on the square root of beta, but okay. Only high pass and band pass filters are possible. So these two first classes of the negative feedback, they are only showing how to design our Biquads, and next time we'll continue with class 3. This is the third class of the negative feedback, and we will see what will happen with these here position of poles. So poles will be here, somewhere or here. So it is good to know where are the poles. This is for now so much, but when we finish all this, it will be to us more obvious. Now I will ask you, do you want to ask some questions before we finish today? Do you have some questions?
No. It was clear.
It is everything clear to you? Before we finish, I must show you one very important book. This book here. You have this book on your materials. If not, tell me, send me mail, I will send you. So here in this book, chapter 8, speaks about these our slides. So this what I have explained just now, you can read in the book. So probably it is, so this is class 1 and class 2, exactly what I have shown you today. So this is probably good for you to understand if you don't understand what I'm talking about. Also here you have introduction to signal flow graphs. So you can also try to understand signal flow graphs. So here are our examples, if you remember. So these two topics that we were learning today, you can find in the book under chapter 5, and we have just now started chapter 8. We jumped over chapter 6 and chapter 7, and you will see soon that it will be becoming more and more interesting. Of course, this book is very big. I don't suggest you to learn all the book, but just few chapters which I show you. So this is the second important book. Last time you have learned from the book of Van Valkenburg. This book is from Moschitz, and you have it, of course, in your materials. Okay, here in the preface and in the acknowledgements you have, I'm deeply grateful to Dr. Dražen Jurišić. So my name is here in the book because I was contributing to this book to become possible. Okay, so if you have some questions, please tell me. If not, then we will see us next week at the same time, and we will have again 2 hours. It is enough. And then we will continue with this topic, and then we will not do every detail, but just to have feeling what's going on, and then we'll start with some examples to prepare for the examination.
I have one question.
Okay, just
we did not have any midterm exam, so our only marks will be the final exams.
Okay, that's it. No problem. It's not complicated if you didn't have. So okay. This was organized by Professor Lackovic, the first part, but I was talking with him, so it will be good.
Okay.
We will organize it. So the most important thing is here in this Erasmus exchange, this course of Amos, you have books. So just concentrate on this, what we are teaching on the lectures. Do you have some more questions?
That's it.
Okay, if not, I wish you good weekend, and that we'll see us next Friday at the same time, and they will continue. Bye-bye.
Okay, bye.
Bye.